There's this introduction to continuous variable to CV quantum computing. Let's just do that, which is basically the one that is in the paper that is related to the project. So I'm going to try to scan that. Where am I here? So I'm going to try to go through that appendix and then see if that gives me a better understanding or sort of another perspective to this. So most of the things built in universal quantum computer have been directed towards creating a discrete quantum computer that uses 2 quantum bits. In a similar vein to a classical computer using 2 classical qubits in this approach. The quantum equivalents of bits are implemented using discrete quantum phenomena such as electron spin. This scheme is called discrete variable quantum computing. In CV quantum computing, we're not restricted to discrete values, but we can have continuous values as well. For the purpose of this paper, we define the state of a continuous variable of a CV quantum computer and some operations in those states. Okay, so Q modes. We know I checked in my previous video the Xanadu thing. So Q modes are sort of the equivalent to qubits in classical computing. There's a bit, the discrete variable computer, continuous. The Q mode is the basic computing unit. As a physical system, we can use a quantum harmonic oscillator as a model that allows us to investigate the state of continuous variable quantum systems. In general, for each state of the system, there is an associated Q mode. In general, for each state of the system, there is an associated Q mode. Therefore, we make no distinction between state and Q mode when there is no risk of confusion. Mathematically, if this system has a Hamiltonian, then it's described by the following thing. The Hamiltonian H denotes the Hamiltonian of the kth harmonic oscillator among n Q modes. Okay. From elementary quantum mechanics, we know that the Hamiltonian of the quantum harmonic oscillator is given by these. So the Hamiltonian thing is basically what describes the energy of the system. So this is just saying the Hamiltonian of the system is the sum of the Hamiltonian of the Q modes, the energies of the Q modes, and that's the definition. And frequency. Okay, quantum harmonic oscillator. So this is probably what's kind of used under the hood, and that's why. So you've got whatever that formula that defines the Hamiltonian, and then you have the position and the momentum operators. Okay. May obey the commutation relationship, whatever. We introduce 2 new sets of operators defined in terms of x and p. Quadratures of a single Q mode are defined as follows. X, P. The Hamiltonian can be defined in terms of these quadratures. Okay. So we've got position and momentum. Whereas in the discrete quantum computing, you've got the amplitude and the phase. Vacuum state. There exists a special state that corresponds to the lowest energy. Okay, this state is important because coming from classical mechanics, we assume that the vacuum has no energy. But in quantum mechanics, the vacuum actually has energy, and we must make that into account in the CV quantum computing. If we send a photon in one port of the beam splitter but not the other port, our analysis must treat that unused port as a vacuum. Whatever that means. Gaussian states and operators. A certain class of states, the so-called Gaussian states, are extremely important because they are easy to efficiently produce in the laboratory. This is important because while we know that Gaussian states are not enough for universal computation, we still want to investigate what can we accomplish with them alone that we cannot accomplish classically. In this section, we introduce and describe Gaussian states and Gaussian operators. Gaussian functions are proceed to the distribution and finally developed by the Gaussian states and operators. Gaussian functions, found under the name of normal distributions in mathematics literature. Gaussian functions occur with striking regularity throughout science. A phenomenon whose state is described by a Gaussian function, the vacuum state. Okay, so Gaussian functions are just this. We invite the reader to keep from the function in their mind, the form. To keep the form of the function in their minds, okay? So the form, in this case, the way this is depicted here, Wigner functions on the quantum correction. Eugene Wigner formulated a function which is quasi-probability, which is a quasi-probability distribution for multiple particles. If the solution of the state in a given, if the solution to the Wigner function for a particular quantum state in a given basis has the form of a Gaussian function, we say that such state is a Gaussian state. So the system is in a Gaussian state. Okay. So Gaussian states occur in three main ways: as pure coherent states, as pure squeezed states, or as squeezed coherent states. Okay. Coherent states are states of minimum uncertainty, equally dispersed among the quadratures. Still don't know what the quadratures mean in this case. They are created by applying the displacement operator to a Q mode in the vacuum state. This means that the vacuum state is also a coherent state because it can be obtained by applying the displacement operator to the vacuum material. So coherent state has the minimum uncertainty. So the displacement operator maybe, I don't know, maybe just touches the position of the photon, and that still makes it coherent. Squeezed states refer to the states where the quantum fluctuations in one quadrature are reduced at the expense of an increased uncertainty in the conjugate quadrature. I think maybe those quadratures are just sort of like visually like four spaces where the photon can be, I don't know. Squeezed state is created by applying the squeezing operator to a Q mode. So with the squeezed state, you basically, what you do is you so you reduce the fluctuation between quadratures, but you increase the uncertainty on the other side, or something like that. Squeezed coherent states refer to the states that have the displacement operator applied to the vacuum, followed by application of the Q. Okay. So you've got coherent, squeezed, and squeezed coherent Gaussian operators. An operator is Gaussian if it transforms a Gaussian state into another Gaussian state. Okay. The displacement operator increases the measured position by. Okay, so it displaces literally the position, the photon, and the measured momentum. So it touches both the position and the momentum. Momentum using a complex number. Its action on the position quadrature is given by this. Its action in the momentum quadrature is given by this. So in matrix form, taking half and replacing the identity matrix with 1, the displacement operator acts as follows. So it adds an offset in both position and momentum. Okay. The squeezing operator. The squeezing operator with squeezing parameter R reduces the uncertainty in either position or momentum well below the standard quantum limit, while increasing the uncertainty in the conjugate variable. Okay. So what it does is the squeezing operator basically it reduces uncertainty in position, but it increases uncertainty in momentum. And maybe this is just all kind of following also the same set of limitations and concepts of Heisenberg's uncertainty principle. That's like you cannot you cannot know from given two things you want to know about a quantum element. You cannot know one without spoiling the other, or something like that, right? So the idea here is you cannot know about everything. So if you're reducing uncertainty in one side, you're increasing uncertainty in the other side. So that's kind of what this seems to me. The squeezing operator basically reduces uncertainty in either position or momentum, but then increases the uncertainty in the other variable. So there's action in the momentum. I keep reading the word quadrature, and that's something that bothers me because I don't know what it means. The rotation operator rotates quadratures in phase space by this. Its action on the position quadrature is this. Its action on the momentum. What is a quadrature? In CVQC CVQC quadrature. What is this? Yeah, good luck. What is a quadrature? What is a quadrature? Maybe they'll explain that. So the rotation operator, it basically rotates momentum and position. Yeah. Yeah, it seems like it's rotating the momentum and the position, whatever that means. That it's rotating. I don't know. Action position and momentum as follows. Where is the real value? Okay, the beam splitter operation. Beam splitter operation is a two-mode operator that requires two Q modes to operate upon. It may be understood as a rotation between two Q modes. Its action on the position quadratures is as follows. Okay. And its action on the momentum quadratures is as follows. So it touches both variables. I don't understand any of the mathematics. Like I don't understand most of the notation. So don't be. It's like even if I'm silent, I just don't. It doesn't mean that I understand that. Imagine if the beam splitter acts like that. Why there's four things here: x, x1, x2. Ah, okay. So the two positions and the two momentums. Okay. Okay, but intuitively, you've got basically the idea here is that instead of taking a look at amplitudes and spins, which they say they are discrete. So the CV quantum computing takes a look at position and momentum, which are continuum. Okay. The squeezing operator, the beam splitter operator, non-Gaussian states and operators. We will not have much to say about non-Gaussian states nor about non-Gaussian operators, but mention two non-Gaussian operators and technical challenges around their implementation. Non-Gaussian states are simply ones where the Wigner function does not result in a Gaussian function. They can be created when non-Gaussian operators act upon Gaussian states. Gaussian. I hope I'm pronouncing them correctly. The ones that do not return. Okay. Cubic phase operator. The cubic phase operator can be understood as the result of the following process. Prepare two Q modes in the vacuum state. Apply two-mode squeeze operator on both Q modes. Then apply a large momentum displacement on the first Q mode. Lastly, perform a photon counting measurement. What the fuck am I reading? Sorry, on the first Q mode. Okay. This results in the second Q mode behaving as if the cubic phase operator was applied to it. And its state may be called the cubic state, which is an Gaussian state. So what? Oh my god. So two-mode squeeze operator on both Q modes. So remember the squeeze was it either reduces uncertainty in either position or momentum and increases certainty in the other one. Then you apply a large momentum displacement on the first Q mode. Lastly, perform a photon counting measurement that we don't know what it is. But because we're measuring, it seems like that's again then affecting the first Q mode, and it's like no, it affects the second Q mode because we're doing the measurement on the first Q mode. Behaving as if the cubic phase operator was applied to it, and its state may be called a cubic state. It's actually so it affects position and momentum as well, right? But I don't know. Kerr operator. Let this be defined in terms of the quadratures, and it's called the number operator. N is called the number operator. We then proceed to define the Kerr operator with reference to the number operator with parameter. This. Whatever. So the non-Gaussian ones, they do weird stuff on your Q modes. Measurements. Measurements in continuous variable quantum computing, we have an array of measurements we can choose from. Photon counting. My question is again, do those measurements? Because in discrete quantum computing, basically I'm of the opinion that the measurement basis and the measurement is not like you've got one measurement. I mean, you choose the basis in which you want to measure, but it doesn't really matter because at the end of the day, you're observing the same system. So if you want to, you can move stuff around. I mean, the way you measure in different bases is just by manipulating the information and applying gates before performing a Z measurement. So everything can be defined. All the other measurements can be defined on like with the Z measurement, and then here it's this photon counting measurement projects the Q mode into the number eigenstates and resulting in a natural number. You know what? I'll have to do maybe some quick search on eigenstates and eigen stuff because it's being measured everywhere, and I'm not really super familiar with the concept. In a natural number n, for n equals 0, photon counting of a single Q mode in a multimode Gaussian state preserves the Gaussian character. Homodyne detection. Photons are captured by a photodetector which converts photons into electrons, resulting in the electric current. This electric current is generally proportional to the number of photons. We wish to detect the quadrature of the Q mode under consideration. To accomplish this, the Q mode is combined with a 50-50 beam splitter. The two output Q modes of the beam splitter are the ones that are converted to photocurrents. The quadrature is measured. It's a projective Gaussian measurement that projects Gaussian states onto other Gaussian states. Heterodyne detection is a measurement of both X and P quadratures simultaneously. This results in uncertainty in the measurement of quadratures. As with homodyne measurement, the heterodyne measurement projects. Okay. Oh, what is all this? The plots of loss function. Okay. Okay. Parameter value. Cubic phase gate parameters converge. Okay, those are actually, okay, this is actually stuff that it's, so that was it about the introduction. So literally, this seems to me, and maybe it's enough. I think in the next video, I'm just gonna go back to the code. So basically, no, I said I will take, okay, I'll do another video and I'll take a look at some actual algorithms, like small scale algorithms, to try to understand how those gates and states and all that stuff is playing around. But I think I get the gist of it, which is basically, yeah, so you have, instead of amplitude and phase, you've got momentum and position, which are continuous variables, and then you've got a different types of gates you can apply, which modify those elements, and then there's certain types of states that there can be called Gaussian states. It's not all the possible states you can get in, but the Gaussian states seem to be sort of easier to manage, or I don't know. They say it's not everything you can do. You can also create fancier states, but then I think that's enough. So it seems I have sort of a clearer picture right now. I don't understand any of the mathematics behind this, literally zero. But I think I got a sort of a rough intuitive idea. And what I'll do next is I'll take a look at so Xanadu. I'll take a look at some of the algorithms that you can find in the documentation here. Where's documentation and introduction? Quantum gradients. This is what I was taking a look. Quantum gradients. This is the one that I read about when I was struggling with the concept of the quantum gradient. Okay, introduction. So that's not what I was reading. That's not what I was reading. Where was I before? Wasn't it Strawberry Fields or something like that? Oh, come on. Features getting started. Key concepts. I cannot find the anyway, I'll go back to, this is Penny Lane, Strawberry Lane. No, strawberry fields. No. Blackbird documentation. That's where I was. Strawberry fields. So that's. Is it spelling then something? Is it Xanadu doing both types as well? Seemed like. Okay. Here's where I was. Introduction, and this is what I read. And so there is some quantum algorithms in here. Exactly. State teleportation, gate teleportation, Gaussian cloning. I'll probably go with state teleportation because maybe it's similar to. There's also another example. Maybe I'll do that. I'll do state teleportation here, and I'll try to compare that with the discrete quantum computing version of qubit teleportation, and see if that makes kind of sense as well. That's going to be the next video, and then we'll go back to the code. Actually, I think it's good enough. Perfect.